Okay, covalent bonds, again, are the type of bonds where electrons are shared between atoms, and we actually have two kinds of covalent bonds. We have pure covalent bonds, and for pure covalent bonds, we have the electrons being shared essentially equally between the atoms. For polar covalent compounds, the electrons are shared, but one atom has a stronger pull on the electrons than the other atom, so the electrons are shared unevenly between the atoms. For polar covalent bonds, because the electrons are not shared equally, that means the end that has the electrons closer to it is going to be slightly more negative, and the end that has the electrons further from it is going to be slightly positive. These are measurable. If we put hydrogen fluoride in an electric field, we can see this. So on the left side of the diagram, we have hydrogen fluoride molecules. The hydrogen end of the molecule is the slightly positive end. The fluoride end of the molecule is slightly negative end. In just a regular container, you can see that they rotate and are oriented in pretty much any direction. They're very random. If we now put an electric field so that we have one side of our container being negatively charged, the other side of our container being positively charged, what we see is the hydrogen fluoride atoms line up. They orient themselves so the positive portion of the molecule is closest to the negative side of the container. The negative side of the molecule is closest to the positive side of the container. So if we put compounds in a container where we can charge the walls positively and negatively, and if the molecules rotate, then we can identify or confirm the fact that we know that they're polar. Electronegativity is another thing we're going to take a look at. Essentially, electronegativity is the ability of an atom to attract electrons within a bond. Remember, we have talked about electron affinity. Electron affinity is the ability of an atom to attract free electrons. Electronegativity is the ability of an atom to attract electrons within the bond that it forms. Okay, measure the hydrogen element bond, and then I'm going to calculate the hydrogen atom element bond using the equation below. So to calculate the hydrogen element bond, I'm going to take the hydrogen-hydrogen bond energy. I'm going to take the element-element bond energy, add those together and divide by 2, and that will give me the calculated hydrogen element bond. And I'm going to take the difference between the measured and the calculated bonds, and that is my electronegativity. There's a table of electronegativities in your book. Looks like this. The elements on the right side tend to have higher electronegativities. The elements on the left hand tend to have lower electronegativities. You will need to know several of the electronegativities, essentially from memory. And the ones that you're going to need to know are fluorine, oxygen, nitrogen, carbon. And if you look, they go down stair step 0.5 at a time. So it's 4 for fluorine, 3.5 for oxygen, etc. down the row. You'll also need to know chlorine and hydrogen. And if you know those 4 electronegativities, and if you know the trend of electronegativity, you should be in good shape. And the trend for electronegativities, as you see, is shown. As I go left to right across the periods, electronegativity increases. As I go down a group, electronegativity decreases. So when I have polar covalent bonds, bonds where the electrons are not balanced in their bond, I actually can get 2 different kinds of molecules from that. And the different types of molecules I can get depends on the geometry of the molecules. This arrow with a plus sign at one end is called a dipole. And the dipole essentially is the way we represent a polar bond within a molecule. The arrow points towards the negative end, the plus is the positive end. So it's pointing towards the direction that the electrons have shifted within the bond. So dipole is a polar bond. Dipole moment is the net direction of positive to negative charge for the whole molecule. So hydrogen fluoride is easy. There's only one bond, and so the dipole and the dipole moment are the same. We can measure this. They have devices for measuring dipole moments. And for water, it gets a little more complicated. So water is not a linear molecule. Water has a bend or an angle between the 2 hydrogen-oxygen bonds. Hydrogen tends to be the more positive end of the bond. Oxygen attracts the electrons more strongly, has a higher electronegativity. So in 3 dimensions, so if I draw the water molecule like this in 2 dimensions, I can see that the positive end is towards the left, towards the hydrogens, and it's actually a space between the hydrogens. The negative end is approximately where the oxygen is. So I essentially am doing vector diagrams, vector addition when I do dipoles to find the dipole moment. For nonpolar molecules, I can still have polar bonds, but the dipoles cancel. Carbon dioxide has polar bonds. But because it's a linear molecule and the dipoles point in opposite directions and are equal in size, they cancel each other out. And so carbon dioxide, even though it has polar bonds, is a nonpolar molecule. And so we have two molecules here, one that definitely has polar bonds, carbon dioxide, the other that has very slightly unequal distribution of the electrons in the bonds. But they are nonpolar molecules because the dipoles cancel. In your first year chemistry, you learned about using the difference in electronegativities to determine whether a compound bonds were ionic or polar covalent or nonpolar covalent. That essentially is a simplistic way of doing it. What essentially we do is look at the percent ionic character for a bond to determine what kind of bond it actually is, covalent or ionic. Percent ionic character can be calculated if you know the measured dipole of a bond, and you can figure out the calculated dipole moment of the bond. If you take the ratio of those, that will give you the percent ionic character. Okay, if we look at this chart, what we have is the electronegativity difference between the two elements in the compound along the bottom, and we have percent ionic character as a vertical axis. And if we take a look at these compounds, what we use when we talk about electronegativity difference is a difference of about 0.67, or about right here. So compounds that have electronegativity differences less than that are described as having nonpolar bonds. If it's between 0.67 and about 1.67, it's described as having polar bonds. And if the electronegativity difference is bigger than 1.67, we describe it as being an ionic bond. The reason we do that is, if we look, they're kind of grouped in lower left-hand corner, upper right-hand corner, and essentially our dividing line is not that, but percent ionic character. And it turns out that 50% ionic character is what determines more correctly whether something is ionic or not. And what experience and experimenting has shown that compounds that have more than 50% ionic character are defined as being ionic compounds. So ionic compounds are defined necessarily based on bond nature. They're also defined by whether or not when they dissolve in an aqueous solution they form ions, or when they dissolve in a molten state they create ions or conduct a current. In both the aqueous state or when it's molten, the compound ions are free to move, and in order for something to conduct electricity, the ions need to be able to move from one side to the other.